Derivations you may need presence. Consistency of Ampere's circuital law. Using displacement current. Consider a circuit of air capacitor connected with a DC source. Increase the space between the plates of capacitor for better understanding. We know how to use Ampere's circuital law. If you don't know or having problem in it, check out my video on it in my channel. I will provide the link in description. Consider 3 loops in yellow color. One loop is just before the capacitor, one between the capacitor and one after the capacitor. Applying Ampere's circuital law on this loop. Applying Ampere's circuital law on this loop. Applying Ampere's circuital law on this loop. Therefore, Ampere's circuital law is inconsistent in region of capacitor plates. Ampere's circuital law is inconsistent means that it should have given the value μ0I like others, but it didn't. It should have given because the circuit is closed and thus, I current should have also flown through the region between the capacitor plates and we must have got μ0I like other, but it didn't as current does not flow through air. So, Maxwell introduced the concept of displacement current to keep the consistency of the Ampere's circuital law. So, let's first see what is displacement current and then we will continue our discussion. Let's understand what a displacement current is. Let us connect a capacitor to a DC source. Now one of the plates will be positively charged and the other negative. The positively charged is the one connected to the positive end of the battery and the negatively charged is the one connected to the negative terminal. Let's have this enlarged view of the capacitor. Since one of the plates is positively charged and the other is negatively charged, we can say that there is an electric field inside the capacitor. As time passes, the positive charge increases and also negative charges. Therefore, electric field intensity also increases. Thus we can say that the electric field E depends on time t, so we will call electric field E as time-varying electric field. Thus electric flux changes and an current must come into play. Let's say this current ID, this current is actually displacement current. Thus we define displacement current as displacement current is that current that comes to play in addition with conduction current whenever electric flux changes due to time-varying electric field. We usually denote displacement current as ID. Now you might be confused with the term conduction current. Conduction current is nothing but the current that is flowing in the wires and charging the capacitor. We denote it as IC. Now remember one thing, displacement current is not actually a current but acts like current. Maxwell introduced this and said that it only adds current density to Ampere's circuital law and it is called current because he found that if he placed a magnetic needle between the capacitor plates, the needle showed deflection. He concluded that there must be a magnetic field between the capacitor plates due to which the needle deflected and magnetic field must have generated due to a current. So, displacement current is called current. Since it acts like a current, it must have same dimensions as that of current and he made calculations from the basic formula of current. Multiplying and dividing by epsilon 0. From Gauss's law of electrostatics, we know, electric flux is equal to the ratio of charge and epsilon zero. Thus, current can be written as epsilon zero times the rate of change of electric flux. He called this as displacement current. It has the same dimensions as that of current. After the introduction of displacement current, Maxwell added a modification to the Ampere's circuital law. He said the total current is the sum of conduction current and displacement current. This law is known as modified Ampere's circuital law or Maxwell-Ampere circuital law. This law has the property of continuity. Let's understand its property of continuity. Let's again see this diagram. Applying the modified Ampere's circuital law for this loop. Later I will apply for other loops too. Through this loop, only conduction current passes and thus only conduction current remains. We know that the conduction current is equal to the rate of flow of charge. Putting this value in the former equation, we get μ0 into dq dt. Now let's apply for the second loop. Here only displacement current is there and so IC is 0. We saw earlier the expression of displacement current and I have shown it from dq dt, so displacement current is also equal to dq dt. Putting this value in the former equation, we again get μ0 dq dt. For the third loop, the result will be same like that of the first loop as only conduction current passes through it and thus here also we get μ0 dq dt. Thus, we get same equation after applying modified Ampere's circuital law and now the Ampere's circuital law became consistent after modification by Maxwell. If you have any problem with Ampere's circuital law, you may check the video about it on my channel. Link is in description and also on end screen.